Hey, what's up? Welcome back. We're solving another Advent of Code problem for 2022. This is day 19. We're going to solve it with Ruby. This one's called Not Enough Minerals. In this case, we're going to use some blueprints and we're going to make some robots with different minerals that are available. And in order to solve this, we're given lots of different potential blueprints for a factory of robots that are going to generate special kinds of robots that ultimately, I don't know, they're going to help us somehow. They're going to save us somehow. We get our input. It's going to look something like this, where we're going to have a blueprint and some ID for the blueprint, and then how much it costs to build a robot. We're going to have an ore robot that we can build with 4 ore, clay robot we can build with 2 ore, obsidian robot costs 3 ore and 14 clay. I don't know, it reminds me a little bit of Settlers of Catan or whatever, the game. And then each geode robot costs 2 ore and 7 obsidian. That's just for blueprint 1. For blueprint 2, it's going to have different values and costs and spends and all of that. And we need to use these blueprints and figure out which blueprint is going to be the best one. And so in order to do that, we have 24 minutes. And at each minute, we can use a robot to mine the thing that it's specialized in. So we can use an ore robot to mine 1 ore. Or we can build a robot with the factory and have that spit out an ore. This is going to be like another one of those problems where we want to go down a bunch of different paths and find the optimal solution. Each path in this case is going to be, let's go down and build blueprint 1, figure out how many geodes we can get out of it. Then we'll go down blueprint 2, figure out how many geodes we can get out of it, so on and so forth. This first section, it says, if you were to take blueprint 1, here are some things that you might do. So you might start collecting ore and collect some more ore, and then we're going to spend some of that ore to create a clay collecting robot. And then the next time we have 2 robots that are working, one is collecting ore, one is collecting clay. And then in the next several minutes, we're going to start building up enough ore and clay in order to build an obsidian collecting robot, and so on and so forth until we have geode collecting robots, which will collect geodes. And at the end of the 24 minutes, we want to know what the quality is of all of the different blueprints. And the way we figure out the quality is multiplying the ID of the blueprint number with the number of geodes that can be opened in 24 minutes with that blueprint. Okay, so let's grab our input here. So we'll grab these 2 blueprints and we'll paste them in. And in the actual input, they're not going to be on new lines like this, but it'll be helpful to start off like that. We're going to say, no arguments, then we're going to be running against the test use case. Data is going to be data.readLines chomp true. Otherwise, data is going to be file.readLines of argv.first chomp true. Okay. Now we want to get our blueprints. Blueprints is going to be something like this. We're going to say data.split on, we'll split on new line or on a space and on a colon. I think that should give us something pretty nice. So for now, we'll just like p blueprints of data. And we actually want this to be all on one line, but it can be, I don't know, it's handy to see it. We'll just say data.first Ruby day 19 argv.empty Ruby day 19. Okay, so this is what it's going to come out like. We'll have blueprint, then 1, then each ore costs 4, each clay costs whatever. Okay, we could use regular expressions, or we could, let's just grab this whole thing, open up Rubular, and create a regular expression for this. It's going to be, whoops, I didn't even grab it all. Let's just use our actual input first. We'll just grab one of these. Actually, 2 of them just to make sure we're okay. And then we're going to grab another one of them, make that our regular expression, capture group for the cost of different things. Robot costs 4, each clay. Okay, blah, blah, blah. All right. Okay. All right, now we need to figure out what the IDs are. Each ore robot costs or robot, or each clay robot costs clay robot, or. So I'm gonna, the suffix here is gonna be the material that we have to use to buy that kind of robot. And then obsidian robot costs some amount of ore and some amount of clay. Obsidian robot ore and obsidian robot. And then each geode robot costs some amount of ore. This is going to be a geode ore and geode obsidian. All right, so that should give us a match thing that we can use. We'll just say match is this giant regular expression dot match line. So data.each do line. And we'll get some giant match back. Let's actually map it. And then we want to create a dictionary or something that keeps track of all this stuff. We'll say the ID is the match ID. The robot ore is robot ore. Clay ore, obsidian robot ore, obsidian robot clay, geode robot ore, geode robot obsidian. And that should be all of our matches. Okay, we're going to come back and we will add something fancy here that will be helpful for speeding up our algorithm. We'll do that later. Let's print out what our first one looks like now. Blueprints, data, and then we'll pull this up all in one line, run it. Okay, so now we have these two objects or these two dictionaries that have the keys of ID or robot or clay robot or obsidian robot or obsidian robot clay, etc., etc. And let's actually just change robot in all of these. Oh gosh, whatever. I was just going to make it bot because it'll shorten it a little bit. Clay bot. All right, whatever. Okay, that's good enough. Okay, once we have our blueprints, we want to iterate over each of the blueprints and we need to figure out all the different options. Okay, let's just make a new method here called max geodes. And this is going to take in a lot of arguments because we need this to handle all of our different stuff that we're passing in. First of all, it's going to take in the blueprint, the current blueprint. It's just going to take in one at a time. It then is going to take in how many ore robots we have. That's going to be a number of ore robots, clay robots, obsidian robots, geode robots. Then we need to know how much ore we have, clay, obsidian, and geodes, like how much we have of each of those things. And then finally, we need to know how much time we have left. And in order to find the max geodes, we're going to again use something like max is equal to 0. We're going to ultimately return max. And if we have enough money to buy an ore robot, we're going to recurse. We also could just do nothing. Like we could purchase no robots and figure out how much ore we would get, clay, obsidian, and geodes based on our current robots. Maybe we want to say something like, instead of max is 0, what if we make max geodes of all of the same stuff? We're going to pass in our blueprint, our ore robots, our clay robots, obsidian robots, geode robots, our ore, clay, obsidian, geodes, and our time left -1. We don't want to increase our geode robots, but then each of our resources are going to increase by the number of robots that we have creating that resource. This is going to be like our ore is going to go up by the number of ore bots we have, and the clay is going to go up by the number of clay bots. Obsidian is going to go up by our obsidian bots, and geodes by our geode robots. Okay, so this is the base, one of the base cases, right? Is that we don't actually buy any robots and we just keep recursing. Now, if time left is 0, then we want to return geodes, because that's how many that we have found once time is expired. Okay, otherwise, then we have a few different cases. Can we buy an ore bot? Let's see. If we have enough ore to buy an ore bot, then we can try buying an ore bot, and that's going to be like max is, increase our ore bots by 1 and then decrease our ore by the blueprint. But we also, remember, are going to continue increasing it by the number of ore robots that we have, ore bots. And we're also going to increase clay. We're going to increase obsidian. We're going to increase geodes. And we're going to say that is going to cost us 1 minute to do. Now we're going to do the same exact thing with all of the other kinds of bots. If ore is greater than or equal to the blueprint to build a clay bot, then we want to build a clay bot. Okay. This time we're buying a clay bot or building a clay bot. And in order to build a clay bot, we're increasing, we're going to continue, or yeah, it costs ore to build a clay bot. It does not cost clay. Clay will continue to increase based on the number of clay robots we have. And our ore is now going down because it costs ore to build a clay robot. Next, we'll say, can we build an obsidian bot? If we have enough ore and clay to build an obsidian bot, then we should be good to go. Obsidian bots are going to increase by 1. We'll pass our geodes. We need to subtract the amount of obsidian bot ore and obsidian bot clay from our resources there. And we're going to say that again, we're moving forward in time. Okay, finally, can we build a geode bot? So in order to build a geode bot, we need geode bot ore and geode bot obsidian. And we're going to pass in our blueprint, ore bots, clay bots, obsidian bots. And now our geode bots are going to increase, but now we have to subtract our ore based on how much we spent on our obsidian bot. And we have to subtract our obsidian based on our obsidian bot. And finally, we are done. Okay. Okay. This should give us at least the ways that we're going to fork when we can buy different robots. Now, instead of calling these max, I'm going to call them option. And here we want to say something like max equals option if option is greater than max. And the reason we're doing that is that we want to consider each of these different possible cases as we're iterating. And okay, so this is actually a pretty good start for max geodes. Let's say that we have blueprints.data.first. We'll call this a bprint. And then we're going to call max geodes for this blueprint. And we start with one ore robot that we just found. And let's go 10 steps and see how long it takes. And then we'll print out max geodes for that first blueprint. Okay, option undefined for nil class in max geodes 81. Here we go. I forgot to update all these. Okay, run it again. We get back 0. Why do we get back 0? Oh, maybe this isn't enough steps. Like maybe we haven't actually created a geode yet. So let's go 15 steps. I don't know how many it's going to take to get a geode. 20 steps? Without the caching, which we're going to do next, I'm nervous that it's going to take forever. All right, so while that's running, let's add some debugging. All right, so here, let's add some output that will just print out all of our stuff. We don't actually need the blueprint, but we can print out everything else here that we got as arguments so that we can see how it's traversing. Let's run this again and we get some fun output. Let's look and see. We got the first 4 are going to be our different robot types. Then the next 4 are going to be all of our different resources. So we got 14 ore, 32 clay, 0 obsidian, and 0 geodes. And time is now 1. So this is like the last second at the end. A couple things to note about this. Because we have 5 and 6, we have 5 ore robots and 6 clay robots. Those 2 are just going to keep producing tons and tons of ore and clay. But if we're not actually using it to buy anything, then it's not really useful. And so we only need as many robots as we need to buy the most expensive kind of robot. If we look at our input here at all of these different things, right? And this is an optimization that I saw Jonathan Paulson do. If you haven't seen his channel, go check it out. He's fast at solving these things. If you want to see someone solve it really, really quickly in Python or in C++, go check out his channel. But one of his sort of observations was that if you can look at all of the different costs of things, and you don't need more than how much something costs. So in this case, like the most clay you would need is 14, right? In order to build an obsidian robot. Once you have more than 14 clay, you can't really spend that in a given cycle. You don't need more than 14 clay robots, because at that point you could build an obsidian bot for every single step and you would still not run out of clay, because you'd have 14 clay robots producing 14 and then consuming it every single step, basically. So there are certain limitations we can place on things. Here, one of them that you might observe is that in order to build an ore robot, you need 4. To build a clay robot, you need 2. To build an obsidian robot, you need 3. And to build a geode robot, you need 2. 4, 2, 3, 2. Most ore robots you need in one step is going to be like 4, right? Because if you have an ore robot that's producing 4 ore, then theoretically you could build anything that you want. You could build an ore robot, you could build a clay robot, obsidian robot, or a geode robot. Once we get to 4 ore robots, we can stop going down that path. We don't want to build more ore robots than we need to. And so one thing that I like to do is in the blueprint here, I want to say ore max, and this is going to be the max of the match for the robot ore, the clay ore, or the ore robot, clay robot, and obsidian robot, and the geode or robot requirements. Whichever one has the most ore requirements, I'm going to grab the max of those and use that as my ore max and store that off in the blueprint. That way I only have to do it one time to calculate that. And then I'm going to use that ore max down here. I'm going to say if ore max is greater than blueprint, or the ore robots are greater than blueprint of the ore max, then we don't need to make any more ore robots. We can do the same thing for the others, right? But the others, we only use clay on obsidian robots. So we can just say so obsidian bot clay is the same as the max. So down here, when we're considering building a clay robot, we can say, or we already have enough clay robots to create anything that we want. Finally, do we want to build an obsidian bot? The only thing that needs obsidian is the geode bots. We can say, as long as we have more obsidian bots than the maximum geode bot obsidian, then we should be good to go. And that's like the cost of the obsidian. Down here, should we build an obsidian bot, obsidian robots, and the number of obsidian robots is less than or equal to that? Can we buy an ore? Well, I think I got this wrong. If we have enough ore and clay robots are less than or equal to that, and ore robots are less than or equal to that. All right, so let's see how that runs. Okay, now when we stop and we scroll up, you'll notice that we're getting a little bit more obsidian. That's going to be like the third to last column here, this 111. And we're starting to build up some obsidian. Actually, so before we go too far, one other pattern that you'll notice is that these are the, other than the blueprint, this is the list of arguments that we're passing into our max geode function. It's possible that we have already seen this number of ore robots and clay robots and obsidian robots based on the different forks that we've gone down. It is a good point now to start caching our calls to max geodes. Let's just create a global constant called scene, and this will be a hash. And then we're going to just return scene of key if scene has that key. And the key is going to be everything that was passed to the function except for the blueprint. And then we'll update the scene key and set it equal to max. Scene at the key is equal to max at the bottom so that we keep track of what the maximum was. And we can easily cache and return that. All right, so let's run this again. And we got back 2 pretty quickly. Now let's use 24 and we'll run it, and we're expecting 9. All right, we got back 9, but that was super slow, and that was just for one blueprint. If we were to time this, we're going to get back some output. If you haven't seen time before, you can put time in front of any of these like Unix commands, and that will give you some basic tools for benchmarking. While that's doing that, there is another optimization that we can do. And that is, okay, so that took 16 seconds total-ish and 14, I don't know. So this was like 14 seconds in user space, 15 in system IO stuff, and it used 98% of CPU. It's, I don't know, slow to do one blueprint. And we need to iterate over several blueprints, each giving us those geodes. We need to make this faster. One way that we can make it faster is, again, if we print out the key and just try to build up an intuition about what's going on here, you'll see that we continue to grow in ore, in clay, and a little bit in obsidian. But again, like, we have 20 ore here, but we can't actually use 20 ore. And so if we're looking at a row that looks like this, and we have 4 ore bots, 6 clay bots, 2 obsidian bots, and no geode bots, and we have 20 ore, that is basically the same as us having 4 ore, right? Because if we can only spend 4 ore, then it doesn't matter if we have 4, 5, 6, 7, 100 ore. What matters is that we have 4 or more ore. And so when we're talking about our cache key, if this is varying as it continues to grow, then we're going to spend a lot of extra cycles unnecessarily. So one way that we can improve our caching and our cache hits is by taking the modulo of the maximum required for a given resource, using that as part of our cache key instead of the raw value. That way we have more cache hits, and it doesn't actually matter what's greater than our maximum, like, usable. What I'm going to do inside of our cache key here is say or mod blueprint of max ore, and our clay mod blueprint of max clay, obsidian mod blueprint max obsidian, but max clay and max obsidian don't exist. Maybe we should add those, or yeah, it's not even max ore, it's ore max. And for clay, the most amount of clay that we need is obsidian bot clay. And the most obsidian we need is geode bot obsidian, okay? So now if we print our key, you should notice that it's like modulo, right? So now the biggest it's going to get is the maximum value that we require. All right, so let's run this and see how long it takes. Printing out is going to slow us down. Here, let's remove our print statement and see how fast it goes. Okay, 1 second. All right, that's way better than, so without the modulo, it takes about 16 seconds. With the modulo, it takes 1.6. That's like an order of magnitude difference, right? And it's almost exactly an order of magnitude. So let's add it back in. And what we need to do now is, now that we can figure out the maximum geodes, we want to iterate over all of our blueprints and calculate some value, right? Okay, we need to determine the quality level of each blueprint by applying the blueprint's ID number with the number of geodes. So our quality number is going to be blueprint ID times the max geodes of blueprint. And then we're going to have 1. And this is going to give us our quality. And this wants to know, what do you get if you add up the quality level of all blueprints in the list? Okay, maybe we'll just say sum is equal to 0. Sum plus equals quality. And then we'll say puts sum at the end here. And as we're going through, we'll just say puts, yeah, looking at blueprint, whatever the ID is. Okay, so we'll run this. Okay, blueprint 1, blueprint 2. We got back the number 27. We should have gotten 33. That should have been the quality levels. Okay. So let's run this test again against the second blueprint. Blueprints of data.last. And this should give us 24, I believe. Oh, okay, 12 times 2 should have given us the right answer. Ah, okay. What's going on here is that every time we're calling max geodes, it's reusing this global variable for a hash. And sometimes it's saying, hey, I already have that many ore robots, clay robots, obsidian robots, etc. But the cost for each blueprint is a little different. And so what we need to do is in between each of these, we have to clear out the cache. We need a new cache every time. There's a method called clear on hash. So if you have a hash called A and A has some value in it, and you look at A and it has some keys and values, you can say a.clear, if I can spell it right. Okay, and that will remove all of the values. That just wipes out all the values. What we can do is say scene.clear, and that will reset our cache. So now if we run this again against all of our test blueprints, we should get back 33, and we do. Okay, awesome. That's 33. Now let's run it against our, so we've got to grab all of our input from here. We're going to call Ruby day 19 input. Let's actually time it also. Looking at blueprint 1, 2, 3, 4, 5, 6. Some of them are faster than others, right? Like it's going to be able to figure it out pretty quickly. I think it costs less to generate some of them than others. All right, so we end up with 968, which is our, oh, it's not. 994. Why is that different? I think there's a chance that we're excluding too many. So I'm just going to add one to all of these different use cases, just in case we are jumping the gun too far. By expanding what we're modulo buying, we should capture a wider area just by one. And I think that might do it. Let's see. Oh, also when we're running Ruby, or I'm running Ruby 3.2, which I'm really excited for. Ruby 3.2 is supposed to be much, much faster. And right now, while we're in the preview, I don't know if this is going to be true forever, but you can do --widget to use yet another just-in-time thing that makes it way faster. Yeah, it should definitely, in my experience, it certainly makes it faster than 3.2. There is 9, 3, okay, 9. Okay, so this, that didn't do it. Let's also make this +1 for our ore max, just in case there's more ore that we can create, or if just in case we needed more ore than exactly that max. I don't know. Off by 1 errors. At the end of the day, the number of geodes should not change because these parameters that we're using, or these like heuristics, are just constraining the problem space so we're not going out too far. All right, this was the answer 994. That is the solution for part 1 of the puzzle. Part 2 is you now have 32 minutes. And instead of looking at all of the blueprints, we're just going to look at the first 3. For part 2, this changes up a little bit. Now we're going to look at prints is going to be blueprints of data.take 3. And now we're going to say prints.each do blueprint. And instead of going for 24 minutes, we now need to go for 30 minutes or 32 minutes, which is much longer. And okay, so the way that we calculate this is what do you get if you multiply these numbers together? So don't worry about the quality levels, just determine the largest number of geodes and multiply them together. So we want to just get the max geodes and multiply that. We'll say product times equals, product equals 1. And then we'll p product. And then we just cross our fingers and pray that it's fast enough to actually finish before we go insane. All right, so again, we'll add like a little thing here that tells us that we're printing it out. And again, we need to clear our cache and we should be good to go. Let's run that. Each blueprint is going to take much longer now because now we're going for 32 minutes instead of 24 minutes, which is significantly more in terms of things we can build and bots that we can build and geodes, and the problem space just explodes every time you add a minute. Yeah, for every minute that we add to this problem, we're extending it by a lot of computation. The other thing that's fun to look at is the activity monitor here. We can see Ruby is going to grow in memory as it's starting to build up that scene cache of all the different things it's checking out. It's running pretty hot here, 98% of the memory, and we're just going to let it rock. Boom. All right. With the magic of time and editing, we have finished. This is our answer. It took about 3 minutes, 15 seconds, and that's not actually that bad, right? Like you could wait that long. For, I think it was day 16 for part 2, I didn't wait, but I let it run for 80 minutes. 80 minutes to know whether or not your code you wrote was successful. That was killer. As a web developer, I want that immediate feedback. I got to have that immediate feedback. But so this is day 19 advent of code. Hopefully this was fun and useful. This was a tricky one, another sort of dynamic programming problem where we have to go down a lot of different potential problem spaces, and then we have to try to constrain it in clever ways so that it doesn't explode in complexity. Thank you so much for watching. I really appreciate your time and attention. And yeah, we've got 6 more days, so hopefully we can successfully crank these up. All right, we'll see you next time.